The purpose of this video is to present the process and results of the experiment to the client. Throughout the presentation, team members will describe the methods used for experimentation, decisions surrounding the design of the project, and the results along with their associated uncertainties. Calculations and processes will accompany the uncertainty values. The customer for this project is a group of researchers and physicists. The objective is to build a model that predicts projectile range with drag and uses the model to obtain the optimal launch angle. The model relates launch parameters to the projectile's horizontal range for the purpose of validating the assumed drag coefficient of a non-spinning, dimpled sphere. With this model, the client can predict the range of the golf ball within a suitable confidence interval. The flight path model was generated through experimentation. A golf ball was launched from a pneumatic air cannon at various angles, and the launch velocity and projectile range were measured with the appropriate instruments. The golf ball was encased in a 3D printed sabot to prevent the ball from spinning. Using the results, the team created a model relating launch angle to the expected range. The resulting model has an associated uncertainty that is within the plus or minus 10% margin of error specified by the client. This accuracy makes the model suitable for the customer's intended use. Researchers and physicists commonly use the classic parabolic model to illustrate projectile behavior. The issue with this model is that it does not account for drag, resulting in a less accurate prediction. The drag model end product obtained through this project assists researchers studying the effects of drag. The customer will be able to determine the optimal angle that ensures the maximum range with a given velocity input. Requirements for the model that are provided by the client include accuracy, cost, safety, and no spin. To meet these requirements, accuracy should be within 10%, the cost of materials should not exceed $30, the procedure should prioritize safety, and the projectile should have no spin.
In order to measure our inputs and outputs, we acquired three main tools. To measure the inputs, we used a chronograph for velocity and an error of plus or minus 0.25% and an iPhone measurement app for getting the angle of the cannon within an error of plus or minus 1 degree. For measuring the outputs, we used a laser rangefinder to gather the total distance in yards, plus or minus 1 yard. This total setup consisted of a PVC cannon, a golf ball round encased within a 3D printed sabot, a mount to allow a varying angle of the cannon, and a chronograph placed on top of a camera tripod. Before we test, some assumptions were made to simplify the desired outcome. To prevent unknown forces from acting on our system, the non-spinning nature of the golf ball encased within a sabot simplifies our equations by removing unknown forces. Additionally, the environment was controlled by conducting tests in a similar location, temperature, pressure, and with a minor to no wind. Engineers have conducted their own testing for the equipment used. Due to this testing, the instruments have a rated tolerance within the tool's specifications. Some caveats to these assumptions may increase error of measurements due to the assumptions being a simplification of a complex reality. For non-spinning golf balls, residual spin may still occur due to moments created by wind, changing air density, and other viscous effects. As far as engineered products are concerned, there is an inherent assumption that the product will work as intended. As a note, the chronograph does have a quantization error. However, the error was approximated as 0 relative to the manufacturer's rating, as the sampling rate is rated at 48 MHz. Safety is our number one priority. With this in mind, major variables that pose a safety risk to the environment, equipment, and people are identified. First, injury prevention. We required all personnel to wear proper PPE. Just as importantly, everyone stayed outside of the expected flight envelope. Second, the launcher itself. Since we're working with a pressurized PVC tank, we limited the operating pressure to just 20 psi. This is intentionally low to reduce the risk of catastrophic failure while still providing enough force to launch the ball. Third, misfire protocols. We followed a standardized operating procedure for every launch. The cannon was always pointed safely downrange, and we had clear communication before firing. Finally, equipment safety. All instruments were used strictly within their specifications. We also placed them outside of the flight envelope so that no equipment could be struck by the projectile. Here is our standardized operating procedure for conducting the golf ball launch test. If you would like to read it thoroughly, pause the video here.
This study relates muzzle velocity to distance. Two alternatives considered for measuring velocity were a light gate or high-speed camera in conjunction with precise measurement marks. Though a light gate's resolution is higher than the chronograph, around 5 microseconds compared to 0.13 milliseconds, the resolution difference would not affect the results enough to outweigh the convenience of using the chronograph. The high-speed camera was a viable option. However, the data collection would be more subject to bias error because the velocity of each shot would have to be calculated based on observed position compared to measurement marks. Additionally, it would take longer to evaluate each shot's velocity, reducing the number of data points we could collect in the time we had available. To measure the Canon angle, the group considered using a physical or digital protractor. The group decided to use an iPhone calibrated on the jig made to stabilize the Canon. The jig was checked with a construction level before calibrating the phone, and the phone was calibrated each time before adjusting the angle of the Canon. To measure range, the group considered using an infrared tape measure, wheel tape measure, or a laser rangefinder. The group was concerned that the person using the wheel tape measure would not walk in a perfectly straight line when measuring the distance to the ball landing spot. Though the laser tape measure has better resolution than a rangefinder, to use a laser tape measure you must ensure the laser hits the target. This can be difficult outdoors at long distances because the laser is so faint. The rangefinder allowed for easier distance measurement. Ultimately, the group chose to measure velocity, angle, and distance using a chronograph, iPhone, and a rangefinder. The chronograph supplied high enough accuracy and resolution for the needs of this project and was free to use. Because the chronograph was designed to measure projectile velocity, it was easy to set up and safe to use. The phone level, when calibrated before use, provided enough accuracy for the project and was free and simple to use. The rangefinder is accurate within 1 yard and has a resolution of 1 yard. Again, this suited the needs of the project, was free to use, and easy to implement.
While it would have made our calculations simpler, we decided that we would not apply the ideal model for our projectile motion. Instead, we would assume that drag was acting on the golf ball in flight. This required us to implement numerical methods, specifically Euler's method and Python 3, to produce our more accurate theoretical model. As seen in our results, we were right to assume that drag would have a significant impact on the range of the projectile. While our experimental results rendered a percentage error of up to 25% when compared to the ideal, they rendered an average percentage error of only 4.4% when compared to our theoretical model. To identify our optimal angle, we normalized each dataset about the mean initial velocity as recorded from our chronograph, which was 79.14 feet per second. Then a line of best fit was generated to predict the optimal launch angle within our chosen confidence interval of 95%. To define the optimal zone, a second-order progression was performed to solve for the angular width at which the range dropped by the standard error of the mean across all angle groups. This wide interval demonstrates that the system is highly insensitive to angle adjustments within the optimal zone, a finding confirmed by the width of our confidence bands. Quantifying our ideal uncertainty propagation based on the angle and muzzle velocity and comparing it to the total uncertainty of our range measurements, we find a significant difference between the two. This shows that our major source of error comes from random effects of unaccounted for variables, such as wind or ambient pressure conditions, rather than our instruments.
In conclusion, the optimal launch angle is 37.1 plus or minus 4.1 degrees. For the requirements, the uncertainty associated with the range model is 6.04%, which is well within the required 10% accuracy requirement. Safety was prioritized using personal protective equipment and a standardized procedure. The total cost for the project was $12, fulfilling the $30 cost requirement. One requirement not fully met was the no spin condition. Spin was mostly eliminated, however, friction from the separation of the Sabo round caused the ball to slowly spin. To avoid this issue in the future, Sabo redesigns can improve results. Using spin detection and CFD modeling would allow a better understanding of the Sabo's error sources. Using these two methods, the team could design an improved Sabo that eliminates more spin from the golf ball, increasing the accuracy of the model and optimal launch angle.
All of our chosen instruments suffered from systematic errors, and our chronograph also experienced precision error as seen below. We conducted our test at 4 easily repeatable launch angles. Because we had 4 distinct samples within which we had conducted 10 to 12 trials, we conducted a student's t-test for each. When we noticed the similar means and high margins of error within our sample sets at 30 and 35 degrees, we conducted a 2-sample t-test. This showed that the observed difference between the 30 and 35 degree angle set were not statistically significant. This further supports that our results are highly insensitive to angle changes within or near our optimal angle zone. A reduced chi-square test showed that our experimental data was a conservative fit for a theoretical model. A hypothesis test showed that we were right to assume that the drag coefficient was constant throughout the trial. During our testing, we omitted Fourier analysis because our data consisted of only discrete single-event measurements, making Fourier analysis irrelevant to this experiment. And we also did not include single-sample hypothesis test. Because of our variable muzzle velocity, we were not able to compare each sample mean against a fixed, predefined population mean.